Today we're starting off into Unit 2, so we're going to be looking at the beginning of Chapter 3. In particular, we're going to look at the development of the quantum mechanics model of the atom. So the core competency we're looking at here is being able to describe the electron structure of the atom and how that relates to periodic properties in the periodic table. Specifically, I'm looking at trying to explain the hydrogen atom in terms of the Bohr's model, right? Now, quantum mechanics is a huge, nasty field. I'm not expecting you to get huge mathematical depth at this, but I do want you to understand the conceptual basis behind these models. When we left off on our model of the atom, we had the Rutherford nuclear model of the atom, which showed that we had a very compact, positively charged nucleus at the center of the atom. The rest of the atom was mainly empty space, and the electrons floated somewhere in this empty space away from the protons in the nucleus. And this was all out of the Rutherford Guilfoyle experiment that we talked about in Chapter 2. To move beyond Rutherford's experiment, we have to use a tool that we still use in chemistry today. It's called an emission spectrum. So just like when sunlight gets bent through a prism and turned into a rainbow, any element heated to the appropriate temperature will emit its own light. The difference is it's not going to emit a complete rainbow. It's only going to emit certain lines, certain wavelengths of light from that complete spectrum. This is what we call an emission spectrum. It's also referred to as black body radiation. So this is the emission spectrum for hydrogen. It's the simplest emission spectrum. To give you an example, the emission spectrum for lead looks like this. Note, they can be really complex, they can be really simple, but they do serve as fingerprints. This is actually what we use in environmental chemistry to determine, say, the concentration of lead in a water sample. We'll take a known quantity of water, we'll pass it through what's called a plasma induction device, turning it into a plasma where all the materials in there emit their own light, and we'll be looking for the signature fingerprint of lead, and how much of that fingerprint appears allows us to determine how much lead's in the water, right? There's a lot of math involved, but essentially that's how it works. So the first person who tried to move beyond Rutherford's model of the atom was a guy named Niels Bohr. Now, Niels Bohr was using the emission spectrum as his basis of, okay, we understand that the nucleus is where the protons are, and eventually we add the neutrons into that model. But he thinks there has to be some kind of structure to the electrons. They're just not flying willy-nilly around the atom, around the nucleus of the atom. And the way he explains this is with the emission spectrum. So Bohr's model differs from Rutherford in that it still has the nucleus of the protons. But instead of the electrons flying around willy-nilly, Bohr says they can only fly around at fixed distances from the nucleus. Now, this is a hydrogen atom that he's working with, so it's only one proton and one electron. And he says that what happens in an emission spectrum is that this electron absorbs energy and jumps from one orbit to the next. And then it can absorb more energy and jump to the next orbit. But when it falls down, it has to lose energy. And this loss of energy is a photon, right? So that loss of energy is a photon, and because we know the wavelength of the light emitted, we can determine what the difference in energy has to be between the orbits. And Bohr is able to completely mathematically solve the hydrogen spectrum using this idea. The problem is Bohr's model of the atom works awesome for hydrogen, but it fails at helium. Once you get to a two-electron system, and that's the next element up there, once you get to a two-electron system, you can't solve the mathematics. It just doesn't work. So they had to come up with something different. And this is where we go away from classical physics and we enter into quantum mechanics. So probably the biggest name you have to understand in quantum mechanics is Schrodinger's. Because Schrodinger, yes, the dude from the cat. Right? So Schrodinger is one of the pioneers of quantum mechanics. And he takes Bohr's idea, his original idea, and he says, well, it's not bad. It's that it's incomplete. Bohr's orbits were these fixed shells around the nucleus at specific distances. Schrodinger says quantum mechanics doesn't allow us to have this fixed idea, because quantum mechanics is about probabilities. Down at the quantum level, things aren't definitively one way or another. They are just most probably one way or another. So Schrodinger changes Bohr's idea of orbits into these three-dimensional, what he calls orbitals. So orbitals, what's the difference between orbit and orbital? Well, an orbital is a region of space in which you are most likely to find the electron. So it's kind of a fuzzy boundary. So the difference would be, Bohr's idea would be there is a set distance from which you will always find the electron in the first energy level, and then a set distance you will always find it in the second, and a set distance you will always find it in the third. Schrodinger's idea is, well, there's a region of space in which it's most likely to occur. And then in the second one, there's a region of space in which it's most likely to occur, and the third one, so on and so forth. And these shells get bigger as you go farther away from the nucleus. Note, there's no definitive area where it will be. The only thing that's definitive is where it won't be. You'll notice in between these, the probability drops back down to 0. And that's because there are these areas where it cannot exist, these nodes. And so Schrodinger's idea is, I will give you a fuzzy area of space in which it is most probably found. Where it is exactly in that area of space, you cannot know, because anything you do to measure it affects its position, right? Because the only way you'd find an electron is by, shooting a photon at it or something, and that's going to change its energy, so it affects its position. So Schrodinger's maps Bohr's idea into this quantum mechanical probabilistic reality. He expands this beyond just the one proton, one electron system into accompanying an infinite number of electrons. Realistically, we only have to go up to 118, but it could be expanded beyond the boundaries we have now. And he develops what are called the orbital geometries. Now, these are all mathematical solutions to Schrodinger's equations. I don't expect you to be able to figure out how the mathematics for this work. I'll be honest, I didn't figure it out till my senior year of college. It involved differential equations in third semester calculus and a computer. It's not pleasant, and you'll probably never do it unless you want to go into quantum chemistry or, orbital diagrams or whatever. You're not going to do it. The key point here is there are different types of orbitals. There are the s orbitals, which are the traditional kind of sphere-looking idea. There are the p orbitals. These look like dumbbells, right? One along each of the main three axes. Then there are d orbitals, which get a little bit more complex. And then go down the f orbitals, which are all kinds of weird stuff. The important part is there's only one type of s orbital. There are 3 types of p orbitals, 5 types of d orbitals, and 7 types of f orbitals. So note, the number always increases by the odds. 1, 3, 5, 7. It's important to remember that there are a certain number for each of them, because that's going to become important in our next lesson, which is about how electrons fill in these orbitals. So next time, that's what we'll look at. We'll look at the idea of electron configuration, how electrons are placed around an atom.